For this definition, we start with initial parameters. The first one is module size, which controls the size of this module. As you can see over here, it controls the X and the Y dimension. Next, we have modules in X, which is the number of repetition in the X direction, and modules in Z, which is the number of stacking of these modules. Then we have something called the attractor X coordinate and Y coordinate, which determines where the center of this pattern is being generated. Then we have the randomness percentage that determines how random the spread is. And then we've got a seed factor to give us different options. We take these parameters and create a grid in the X and Z direction. To create the grid, we need to use the square grid option. This requires a plane because we're working in the X and Z plane. We can use the XZ plane. Size comes from here, that's the module size. So copy this, bring it up front, that's the size. For the extent, we have these two parameters. So that gives us the grid. We also need to identify the center point of these cells. So we can use polygon center. And get the center points. Next, we need to identify the rectangle that bounds this grid. This rectangle is going to help us find the attractor point. So to do this, we bring in a rectangle component. Plane for this rectangle is over here. The X dimension can be derived by multiplying module size with the number of modules in X. So we copy this, use a multiplication, and that's X. We copy the same and copy the Z, that's in the Z direction. And now we have the rectangle. This rectangle can be converted into a surface, which can be used with a evaluate surface component. We can reparameterize this. Now we need a point to evaluate. We can use these coordinates, which have a slider attached to it. We're ranging from 0 to 1. So we take these coordinates, construct a point, and use this point. Remember to reparameterize the surface. Now that we have this, if we move this around, notice how it captures the entirety of the surface. We're going to use this point and come up with the attractor logic. For the attractor logic, we need to get the distance between all of these points and our attractor points. What we're going to do is measure all these distances over here. Once we have the distances, we're going to sort them. in an ascending order. Here it's a grafted or a branched data tree, so we need to flatten this. When we flatten this, we get all distances in a flat list. We are trying to sort the points based on the distance, so we need to flatten this as well and use this as an input. And now the output is a sorted list of points based on distance from this attractor point. Once we have these points, let's shake things up. I'm going to use jitter to randomize the points. Now the way jitter works is that you can feed any list to jitter, and it requires a numerical input between 0 to 1. 0 means there is no shuffling and 1 means there is a complete shuffle. So we can use a slider, and rather than using a slider over here, I already have a slider which is the random percentage ranging from 0 to 1. So we copy this, bring this up front. That's the jitter. And for seed, I have a slider ranging from 0 to 100, which can be brought up front. Once we have this list of points randomized based on jitter, we need to get the list length. And I would like to divide all of these points into 6 buckets. So I take the list length and I divide this length by 6. Now the reason I have chosen 6 is because I'm going to have 6 different modules and going to use one module for each bucket. Now you can choose to have 5, 4, 2 or even 1 for that matter, that's up to you. But for the sake of this exercise, I'm going with 6 and round this number because sometimes this can be a non-integer value. So we round it to the nearest ceiling and we use this value to partition the list. Once partitioned, you'll see that all these points have been partitioned into 6 branches. Now that we have these points into 6 branches, we can copy this point into our last step, which is to position a module in all of these different buckets. To position that, I need to firstly create a module. I'm going to use a box center and use the module size. Divide this by 2. And use this as the X and the Z value. And for Y, I'm going to go with 100 for now. And I have a box which has the size 300 by 300, same as a module size. This being the module can be brought up front, and we use these points, and we can use the component called orient to place this module across all these points. Now to do that, we need the geometry, which is our module. We need the source, which is a plane. Now, since this is positioned at origin, we can use an XZ plane, which is positioned at the origin, as our source plane. And for target, we've got all of these points, we just need to position a plane, which can again be an XZ plane at all these individual points. So now when we connect this plane will try and position itself across all these individual planes and also position this cube or this module at all of these individual planes. We position that and you notice that we have our output in 6 branches. Let's just hide all the previous components and just have the brep output. Now to visualize these 6 differently, what we can do is come up with swatches. So I'm going to use 6 different color swatch, and I just did that and merge these into a single list. Use a custom preview, use the geometry and use a list of colors which can be crafted because we want to ensure each of these colors gets listed or gets applied to each branch individually. And when we connect this, we get this output, which is completely parametric in how it responds to these parameters. As an additional layer, we can replace this module with custom modules. So rather than following a single module across all 6 buckets, we can create different shapes for each one of them within the limit of 300 by 300, of course. To do that, I'm going to take the module size. I'm going to use a rectangle and also going to divide this by 2. Use a construct domain. I'm going to create a domain from negative 150 to positive 150. So that's negative 150, that's positive. Connect that in the X and Y. Now when I do that, I get a rectangle in the XY plane. But for now, I need it in the XZ plane. I'm going to use this and now it's in the XZ plane. Once I have this, I'm going to use an offset curve component. The distance of offset, I'm going to set it to 25. And I want this offset to happen the other way. So what I'm trying to do is, let me just set this to negative. What I'm trying to do is create modules, 6 of them like this, each with a size of 300 by 300. So the first one has an offset of 25. For the other, I'm going to use divide domain square, use count of 2, convert this into a surface and use iso trim. Once I use an iso trim, and connect the surface over here. Once I use an iso trim, it divides that rectangle into 4. And then I can use the same offset and what I get are 4 smaller. And for this purpose, let me just hide this. Yeah. So I get these 4 curves. And now I have the main rectangle which is over here. I need to use a combination of the main rectangle and a curve. So this together flattened, if I create a boundary surface, this is one module which can be extruded in the Z direction. Well, not the Z direction, but the Y direction, and I can extrude it by 200, and that's the first module. I'm going to use a prep. I'm going to call it module 1. Now that I have these, I can use list item and extract the relevant modules out of this. Now the list item, how it works would be, let me show you. So I have these curves. If I use the area to get the centroid and use point list, let me just flatten this. Yeah. I'll increase the font. Yeah. So these are placed in this order where it's 0, 1, 2, and 3. Right. So this is 0, 1, 2, and 3. Now it's up to me to make a combination out of this. So for each, I am going to use the outer rectangle, and then which ones would we want from this? So I can have a combination of 1 and 2. I can use this and this together, can give me module 2. But module 1, module 2. I can copy this once again. Actually, let me just increase this and add all 4 of them. So I get this as the second module, this as the third module, for the third module I'll add another one like this. So I have a big space over here, then I've got 4, then 3, and then I can do a combination of 2. So I choose 1 and 2, and just to create some space, let me just move this up. Yeah, I can copy this again, and this time I can choose 0 and 3 because I want this and this. 0 and 3. Connect this, connect this. I get these rectangles, convert them into a surface, extrude. That's module 2, module 3, module 4, module 5. And for the sixth one, I can just use a single rectangle. So I'm just going to remove this, or wait, yeah. So I've got these two, and that's the module. So I've got 6 modules. The reason I have 6 modules because I divided the list of points by 6 so that I can have 6 different branches. If these were 8, I could have worked with 8 different modules as well. So it's up to us how many we want to create. I can merge these 6 into a single list. You may choose to do this parametrically. You may do this directly on Rhino and internalize it. The choice is yours. Hide it. I've got 6 of these. These are the B-reps. I'm just going to call it modules. Copy these, bring them over here, and rather than using a single module, I'm going to use this collection of 6 modules. And because this is divided into 6 different branches. If I want one module from here to get applied to one of these branches, I need to graft this as well. So this gets applied over here, and now when I enable this, you'll notice how it gets applied. And as an additional step, let's also use a brep edges, because the edges are not visible, and we use curve display. So I'm using a human plugin which allows me to preview line weights. This is the geometry. We're going to use a black swatch, and for thickness it's going to be the default thickness for now. Select this, and this needs to be interior, not naked, and there you have it, all these modules. Now let's see if this is parametric. So first thing we want to see is, can we move the coordinate? It takes a while because it's doing all the calculations, it's applying all the transformations, but you can see you're still able to move this around, and this gets updated. You can move this up or down as well. You can randomize the pattern. Or you can simply follow an attractor by keeping the randomness 0. If you do increase the randomness to a non-zero value, like this, you can play around with the seed to get different options. And you can also play around with the module sizes, like over here. Increase them or decrease it. Bear in mind, if you use a really high value, this definition would be really slow. So try to limit this between 0 to 100. And there it is. Thank you for watching. This entire video is available on my Patreon channel along with the grasshopper definition, which looks something like this, which contains the initial parameters as well as the entire definition to create this parametric modular wall. If you enjoyed this video, do like and subscribe to my channel.